Derivatives. It is of very general interest to know a certain parameter at various instants of time and try to finding the rate at which it is changing. There are several real-life situations where such a process needs to be carried out. For instance, people maintaining a reservoir need to know when will a reservoir overflow, knowing the depth of the water at several instants of time. Rocket scientists need to compute the precise velocity with which the satellite needs to be shot out from the rocket, knowing the height of the rocket at various times. Financial institutions need to predict the changes in the value of a particular stock, knowing its present value. In these and many such cases, it is desirable to know how a particular parameter is changing with respect to some other parameter. The heart of the matter is the derivative of a function at a given point in its domain of definition. Definition 1. Suppose f is a real valued function and a is a point in its domain of definition. The derivative of f at a is defined by limit h tending to 0 f of a plus h minus f of a divided by h provided this limit exists. Derivative of fx at a is denoted by f dash a. Observe that f dash a quantifies the change in fx at a with respect to x. Example: find the derivative of the function fx equals twice x square plus thrice x minus 5 at x equal to minus 1. Also prove that f dash 0 plus 3f dash minus 1 equals to 0. Solution. We first find the derivatives of fx at x equal to minus 1 and at x equals to 0. Then, using the first definition of derivative, putting the values in the equation of function f, and finally on simplification, we get the result as minus 1. Similarly, we find f dash 0, which comes out to be 3. Therefore, clearly f dash 0 plus 3f dash minus 1 equals to 0. Hence proved. Now, hence remark. At this stage, we note that evaluating derivative at a point involves effective use of various rules, which limits are also subjected to. Come, let's learn them from some examples. Let's take an example. Find the derivative of sin x at x equals to 0. Solution. Let fx equals sin x. Then, using the first principle of derivative and evaluating the limit, we get the result as 1. Geometric interpretation of derivative. We now present a geometric interpretation of derivative of a function at a point. Let y equals to fx be a function, and let p equals a comma fa and q equals a plus h comma f of a plus h be 2 points close to each other on the graph of this function. From the triangle PQR, it is clear that the ratio whose limit we are taking is precisely equal to tan QPR, which is the slope of the chord PQ. In the limiting process, as h tends to 0, the point Q tends to P, and we have limit h tends to 0. F of a plus h minus f of a divided by h is equal to limit Q tends to P, QR divided by PR. This is equivalent to the fact that chord PQ tends to the tangent at P of the curve y equals to fx. Thus, the limit turns out to be equal to the slope of the tangent. Hence, f dash a equals tan psi. For a given function f, we can find the derivative at every point. If the derivative exists at every point, it defines a new function called the derivative of f. To know how we normally define derivative of a function, let's learn definition 2.